pronounce correctly?
That's right.
Yeah, okay, great. So are you ready? Should we start?
Yeah, I'm ready.
Yeah, okay, good. So let's start. It's the first seminar of this academic year. Congratulations. And so our first speaker is Yash Deshmukh from the Institute for Advanced Study. The title is Categorical and Geometric Enumerative Invariants. So please.
Yeah, thank you. Thank you very much. I'm very happy to speak here, particularly on this topic. So as the title suggests, I want to talk about categorical enumerative invariants and their relations to geometric enumerative invariants. So enumerative invariants in this talk will only refer to Gromov Witten invariants. Okay, so what's my motivation? So the motivation comes basically from understanding mirror symmetry, particularly from the viewpoint of homological mirror symmetry. And so the early successes of mirror symmetry in mathematics came from their applications to curve counting. So mirror symmetry tells you that every Calabi Yau manifold, maybe Calabi Yau threefold, in the most basic statement, comes with a mirror Calabi Yau. And the Gromov Witten invariants of one manifold should be related with the period integrals of the Calabi Yau form on the mirror Calabi Yau. And this relation can be made quite explicit, specifically in the example of quintic threefold. And Candelas, De La Osa, Green Parks used these specific relations to give conjectural formulae for the number of rational curves on quintic threefold, which was open problem for a long time. And later on, the work of BCOV gave predictions for curve counts of genus 1, genus 2, and also some structural relations for higher genus, which also led to a bunch of computations of curve counts, Gromov Witten invariants for quintic threefold. Okay, but one of the dominating approaches to studying mirror symmetry, however, has been this proposal by this conjecture of Costello called the homological mirror symmetry conjecture, which says that the way which expresses mirror symmetry in the following form. It says that the Fukaya category of Calabi Yau manifold should be equivalent as infinity categories with the category of coherent sheaves on the mirror. And this program has been very successful with deep results in particularly in symplectic geometry. And one of the questions one might like to answer is whether this homological mirror symmetry actually implies enumerative mirror symmetry, because enumerative mirror symmetry somehow was why people initially got interested in homological mirror symmetry. So this is the question, that's the motivating question for the story that I'm going to talk about. Okay, so here's a quote from Costello's ICM address, the same address in which he proposes the homological mirror symmetry conjecture. So he tells you what you should do. He says that you should try to define Gromov Witten invariants purely algebraically. So given a category, you should try to construct something like a Gromov Witten invariant for the category. And these constructions, of course, should be so that when you apply the construction to the Fukaya category, you recover the Gromov Witten invariant of the symplectic manifold. And if we successfully do such a construction, then the homological mirror symmetry should somehow tautologically imply enumerative mirror symmetry. So this is the proposal where you just start with a category with some nice properties and you try to assign to it enumerative invariants. So that's the goal of this talk. So here you'll see that I talk about something called cohomological field theory. So cohomological field theory is just an algebraic way of packaging Gromov Witten invariants of a manifold. I'm going to mention it later on in the talk, so even if you don't know, it's fine. So the goal is going to be start with a category which is smooth, proper, and Calabi Yau. All of these words will again show up in the talk. So you start with such a category, and there's going to be some extra data. Spoilers for later, but you start with this category and extra data, and you try to define a cohomological field theory structure associated with this category, which you would expect to mimic the Gromov Witten invariant. So this is the first goal. And secondly, we would want to know when this CohFT, so cohomological field theory is called CohFT in short. So we would like to know when this CohFT that we constructed from the category actually coincides with the CohFT that we define using Gromov Witten invariants. So that's going to be the second part of the talk.
So I somehow missed, what do you call Gromov Witten cohomological FT?
So, I mean, you'll see that there's a comment after I said Gromov Witten CohFT, which is when it's defined.
So you didn't tell us where is it, because the first one actually goal define cohomological field theory for a smooth proper Calabi Yau with some degeneration of Hodge de Rham property. I think it's done. It was done in our paper of 2006 with Maxim and independently by Costello, but it's kind of maybe you have a different construction. But
so I think maybe something to say about cohomological field theory is a priori cohomological field theory carries more data than just the Gromov Witten potential, which would be like the part of the CohFT on the tautological subring. So I think in this construction, I'm going to try to describe just some construction which is kind of topological and actually just gives a cohomological field theory instead of like just a potential. So that's
no. It's not a potential. It's a pretty abstract structure. We did it as I told you, almost 20 years ago. Actually, in fact, 20 years. Yeah, you start with Calabi Yau category of whatever dimension D. Smooth proper with, if you want topological field theory, you can stop. If you want cohomological field theory, you need degeneration of Hodge de Rham. But if you have it, so then in pretty abstract terms, in terms of certain ribbon graphs and action of some prop on the chains, we defined it even at the level of chain. Did you do you know our paper?
Yes,
Probably you should. I mean, everyone knows since kind of.
Yes,
and also Andrei Calderaro with too, they developed some approach to Gromov Witten invariant. I mean, this exactly what what is in your page.
Yes.
To derive Gromov Witten from this abstract story. So then probably you know. The second part is a mystery for me. What's another homological field theory? But the first part, it's pretty kind of it's an old story. Yeah.
I mean, as I understand it, it actually does not define a cohomological field theory.
Yeah, it does. If you read, I mean, if you read our paper, we explain. Maybe we did not kind of provide it because it was the very end of the paper. It's called Notes on Infinity Algebras. Yeah. So it was not really, it was kind of byproduct of more general formalism. But yeah, we explained why. Actually, geometrically, why degenerations of Hodge de Rham should give cohomological field theory. I don't know whether kind of before you anyone worked out the details, but it's not a big deal. But the second one, yeah, it's really interesting.
Yeah, I'm not, okay. Maybe I can describe what construction I have in mind.
Yeah, sure, absolutely. Sorry, yeah, go ahead.
Yeah, I think it's going to be, I think it's just going to be smoothing out maybe some kinks in terms of the construction. But I guess the idea is this cohomological field theory will be constructed so that it will have nice universal properties, which then you can use to make a comparison when a geometric theory is available.
Okay, go ahead.
Yeah, thanks. Okay, so here's just some context for where this construction fits in. So there have been multiple constructions of the same flavor trying to construct things similar to Gromov Witten invariants, purely abstractly, either from categories or otherwise. So here you will see the constructions in genus 0, where on the left-hand side you have the symplectic invariants, on the right-hand side you are supposed to have complex invariants. And the part in orange kind of tells you at least in some cases, tells you the abstract construction for describing these invariants. So on the left-hand side, we have Gromov Witten invariants that are related to period integrals. On the right-hand side, which is the original physical prediction. Then these Gromov Witten invariants were packaged using in the language of Frobenius manifold and fundamental solutions that satisfy some very interesting differential equations like the WVV and string equation and so on. So this was the work of Dubrovin, who studied Gromov Witten invariants in this packaging. And on the complex geometric side, Barnikov and Kontsevich gave a construction of this Frobenius manifold using on polyvector fields of Calabi Yau. So Barnikov and also Ganatra, Perush, Sheridan gave a construction of this Frobenius manifold just starting from smooth proper Calabi Yau categories. So this categorical picture, these invariants in categorical terms are known. Similarly, you could go further and package the Gromov Witten invariants as something called hypercommutative algebras, which are Gromov Witten invariants of genus 0. As hypercommutative algebras, so these are invariants that were, these are structures that were defined by Kontsevich and Manin. And there's a lot of literature in operator theory where people try to abstractly construct these hypercommutative algebras, starting with Gersten-Haber algebra, which is the structure that's supposed to exist on Hochschild cohomologies of the Calabi Yau categories. Okay, so this is a story in genus 0, and this is not an exhaustive list, just some highlights. And I think we know fairly well in genus 0 how this hypercommutative algebra or the Frobenius manifold is to be gotten from the categorical invariants. So what happens in higher genus? So in higher genus, I have listed here two main formalisms to encode the higher genus Gromov Witten invariants. The first one is this Lagrangian formalism using infinite dimensional linear symplectic spaces, which is due to Giventhal and Giventhal codes. And the second one is this cohomological field theory, which I will say what it is, also due to Kontsevich-Manin. So I'm actually not aware of the B-side analogs, but I'm very happy to hear if somebody knows if there are B-side constructions that are mirrored to these formalisms. There are some.
Say it again. What did you say? The last phrase I somehow missed.
I don't know many B-side constructions that are mirrors to this. So, for example, Lagrangian formalism or cohomological field theory. There are some results where these things are constructed using Telemann's reconstruction, starting from a semi-simple genus 0 part, but that construction somehow very formal. So I don't know a construction that's supposed to work in general.
Okay.
Yeah. Okay, and one can ask what are the abstract construction in this case. So maybe starting from a category. So this was Costello, and also what Jan was referring to, these constructions where Costello and also later the work of Costello Calderaro too. They start with a smooth proper Calabi Yau category, and they construct the Lagrangian formalism and give something like Gromov Witten potential associated to a category. But as Jan says, I mean, it's not just a potential, there's maybe more structure. But for now, I'm just...
Yeah, that's true. Also, maybe for historical purposes, you should really add our paper with Maxim, because actually it was even before Costello.
Yeah, I apologize.
But yeah, okay. And also, I don't know, there was much more recent paper by Maxim, Yanis Vlasopoulos, and Alex Takeda. They did this kind of construction for weak Calabi Yau structures, probably you know it as well. So it's kind of...
Yes.
And also there is a type of manin is with just two ends, not three ends. Not manin, but manin. Yeah, okay. Yeah, exactly, yeah.
And so is Soebelman.
Soebelman also was one n, but well, it's forgivable because German always always write 2n, and maybe my ancestor, they had 2 n's. I don't know. All right. Yeah. Sorry.
Yeah, I make a apology in stock for everyone. Spelling mistakes. Okay. Any other questions on just this general story? I mean, I haven't said any math yet. Okay. So if not, I will proceed. So I want to describe this construction to you, and the construction. So what's the plan for the construction? So the construction is going to proceed in 3 steps. So the first one, you start with what's going to be a smooth, proper Calabi Yau category, and then you're going to use this construction of Costello. Also, as Jan pointed out, I mean, there's another construction that came before, which was due to Consoy-Soebelman. So these constructions produce from a category.
What was I? Sorry for correcting. Soebelman, yeah. Because I know how this spells. So. Okay, anyway, what's a positive boundary? You will explain us.
Yes, I will tell you what positive boundary is. But I mean, positive boundary is just going to be roughly it's TCFT with the condition that there's always at least one input. So that's going to be the positive boundary part. And then I'm going to tell you how to remove this condition. So you try to build a TCFT that doesn't have this restriction. And finally, you go from this TCFT to what I'm calling DMFT, because I did not want to call it like chain level cohomological field theory, but that's what it is. It's the chain level version of cohomological field theory, but we are calling it Deligne-Moffat field theory. And this entire story proceeds both in open and closed sectors, so you don't restrict to the closed sector anywhere. So that's going to be the plan for the construction. So let me start by describing what Costello's construction is, but I need to tell you what these structures are. So I need some definitions. These structures are defined as functors out of certain categories, where the Bordism type categories where morphisms are moduli spaces of Riemann surfaces. So these moduli spaces are things that I will describe for next few slides now. So the first category we need is this M-framed open close category. So M-framed here is going to refer to the following fact. We consider Riemann surfaces with punctures, either interior puncture or boundary puncture, but the framing means that there's a there's a choice of either a half cylinder or half strip around the puncture, depending on whether the puncture is in the interior or the boundary. So you have Riemann surfaces with punctures, and around each puncture you have a choice of a holomorphic cylindrical end. Okay, so more formally, this is going to be a category enriched in spaces or stacks, if you want. The objects are going to be pairs of sets, which I'm denoting YO and YC for open and close. So opens are going to be things that are either mark points or punctures on the boundary, and closed are things that are punctures in the interior. So your objects are these pairs of finite sets, and morphisms between two such pairs are going to be moduli spaces of Riemann surfaces of the kind that I show. So as I said, these are going to be Riemann surfaces where you are allowed to have interior Riemann surfaces with puncture. The puncture can be either in the interior or on the boundary. And around each puncture, you have either a choice of a holomorphic half strip or half cylinder, depending on whether it's a boundary or interior point. And of course, these things are divided between interiors and inputs and outputs, as I have shown. So inputs are always on top for me, and outputs are on the bottom. Okay. So you'll see that apart from these inputs, like these closed inputs and open inputs, the Riemann surface also has a bunch of other boundaries. So for example, this purple part, which is neither an input or output, but this thing is just allowed to be part of the curve. So you don't prevent these things. So these are the framed moduli spaces where the framing just corresponds, just refers to the framing near these punctures. Okay, these are the first kind of moduli spaces. Any question about this?
Actually, no, I think that it's exactly what we described at the level. I even found, I downloaded our paper. There is a definition 1161. And we consider isomorphism classes of triples, and the marking is exactly the choice of some semi-annuli things. We called it marking, not framing, but yeah, okay, yeah.
Yeah, I mean,
good,
yeah, these are same spaces, I think. There's no difference.
Yeah, good.
So next, in order to define these things like positive TCFT, there's subcategories. There's going to be some special subcategories. So the first one is what I denote as partial plus. So this is the positive boundary and framed. And the positive boundary just refers to the condition that there has to be at least one closed input or a free boundary. So here are a bunch of examples. The first one has two incoming closed boundaries, so it's good. The second one has no incoming boundary, but it has a free boundary, so that's also fine. The third one also doesn't have any incoming either closed or open boundary, but it has free boundaries, so that's also fine. The last one has no free boundary and no incoming closed boundaries. So this thing is not allowed. So everything except the last one is okay. So this is the positive boundary part where you put the condition that there's at least one closed input or one free boundary. And then you have just the open sector. So these are things where you don't allow any closed boundaries. So both the incoming and outgoing, both the inputs and outputs have to be just open punctures. So these are things that are that I'm going to denote by M-framed open. So instead of M-framed open close, it's just M-framed open. As you see, the first one is fine because all the inputs and outputs are open. In the second one, there is one closed input, so that's not allowed. So this is the open sector M-framed open. So these were things that were for TCFTs and positive boundary TCFTs. Now we come to things that we use for defining DMFT, these Deligne-Mumford field theories. And this thing I denote by m bar open close following the usual notation. So it's the same set of objects, but in this case the morphisms are going, instead of taking Riemann surfaces with punctures, now we are taking stable nodal curves with punctures. The punctures can be either interior or boundary punctures. So these are bordered stable nodal curves, and you are allowed to have interior or boundary punctures. And the input and output boundary punctures have to match with the objects between which you are looking at morphisms.
Yes, and just a short
Yes.
question for the future. When you are interested just in the topological field theory, you don't need stable curves, or you do?
So in this case, I don't put the condition of stability, and the reason, one reason you could argue is the following. So these curves also carry, as I said, I'm considering them with this data of the marking on the boundary, or embedding of a holomorphic end, not on the boundary, embedding of a holomorphic end around the puncture. And if you remember these ends, then you also require the automorphisms to preserve these ends. So, like, for example, if you look at this picture, you'll see that there are a bunch of things. So, for example, this leftmost cap, it looks like it's unstable, but it's actually stable because you remember the parameterization near boundary. So here, I could require stability, but it's not changing anything.
Okay.
But working with DMFTs, I require stability. But you'll notice that there are a bunch of unstable curves that I have drawn in this picture. So these things are just formally, you add these exceptional curves like sphere with 1 mark point, sphere with 2 mark points, and also disk with 1 mark point, disk with 2 mark points. And you declare these unstable moduli spaces to be just points. So I add them, but I take them to be points. Okay. So in all these moduli spaces, I have been telling you what the objects and morphisms are. So what somebody should have asked me is how I compose. So the composition is just going to be gluing of Riemann surfaces in this case of these M-framed moduli spaces, where you have one set of curves and then outputs of this set of curves match with inputs of another curve. Then you just compose these morphisms by gluing the Riemann surface in the holomorphic parameterizations near the punctures allow you to do this gluing unambiguously. Okay, so that's how gluing happens in these M-framed moduli spaces. For M-bar moduli spaces, sorry for switching back and forth. For M-bar moduli spaces, you don't do any gluing. Remember, there are just mark points. There are no parameterizations around mark points in this case. And instead of doing gluing, you just do clutching maps. So if you have one set of curves and another set of curves, you just join them, create new nodes, and you get another stable curves. So there's no gluing that you do. You just create new nodes. This is the composition in this case. Also, another structure this category has is it is a symmetric monadal category. Namely, it has a tensor product. And the tensor product is just given by disjoint union, both on objects and on morphisms. Similarly, M-framed categories also have symmetric monadal structure, again given by disjoint unions. So these are the categories that are going to be used to define the theories. M-framed, M-bar. M-frame has composition by gluing, M-bar has composition by clutching, and both of them have tensor product with disjoint union. Okay. So let's move on. Okay, so here's the definition for this TCFTs and DMFTs, and you will notice that I'm using what one might consider unnecessary generality here in order to do the definition. But the reason is that I want to use some homotopy universal properties of these structures, and these structures, another way to look at them is as algebra Zohr prop, as Jan was mentioning. but the theory of algebras or props does not have a good there's no good model structure to deal with these things. So if you want to use some homotopy property, then you are forced to work in slightly more general setting. So either you can work with just simplicial localization, which are simplicially enriched categories, or you might as well just work with quasi-categories, which is what I'm doing here. So whatever the statements are going to be, this setup, the statements are geometric statements, and this particular setup does not matter. But if you want to use some universality properties that you get out of the construction, you need to work in something like this in order to make your statements correct. So you won't lose anything in the top if you just keep thinking about category, like C being the category of chain complexes considered as a DG category. So there's a precise sense in which this is equivalent, but I won't go into that. If you don't like this infinity category stuff, just think about chain complexes as a DG category or a characteristic zero field. Okay, so you start with some such target category C, which in the more general setting.
So you were thinking of the chain complexes in characteristic zero case. And
Yes.
what might go wrong if in positive characteristic?
I'm not actually sure. I mean, here I'm saying you consider this particular, I'm saying you can work with chain complexes because there is a statement which proves an equivalence between the homotopy theory of DG categories or a characteristic zero ring even, and with k-linear stable infinity categories. I don't know if this equivalence holds more generally. If it holds more generally, then there's
so you're using that condition. Okay. So
yes.
I just want to see what kind of properties of a characteristic zero you need. Thank you.
Yeah, thanks. Okay. So the definitions are fairly straightforward. Open closed TCFT is just going to be a symmetric monadal functor. So functor preserving tensor product from this M-framed open close. Positive boundary TCFT is going to be functor out of the positive boundary M-framed. Open TCFTs are going to be functors out of this M-framed open, and DMFTs are going to be functors out of M-bar open close into some fixed symmetric monadal categories. So we work in the infinity category setting, so you want these functors to be like in symmetric monadal functors in the infinity sense. Okay.
Yes, and when you said universality at the very beginning of your talk, you meant what? That you can take C as as it's in your definition, that it's universal with respect to the category, or you meant
no,
something?
I think so. The universality properties are going to come later. So, for example, as in your construction or Kevin Costello's construction, you do some free extensions starting from a smaller category, and you want to say that these free constructions are initial in an appropriate sense. To make that precise, I need some language, homotopy theory language. That's all.
Yeah, and you will need the model structure later on, or what?
So I don't know the existence of a model structure which will allow us to talk about this. I think there is no general construction of model structure on algebras of a given prop, which is what you would need to discuss these things.
Okay.
I think the model structure is not available. That's why you need to work with something slightly more general.
Okay. Go ahead. Yeah.
Okay, so little bit more abstract nonsense. So C is still this symmetric monadal infinity category, presentable stable. And just like you can talk about DG categories, you can talk about linear categories over C. And even in this setting, you can make sense of these properties like smoothness of categories, homological smoothness, homological properness, smooth and proper Calabi Yau structure, and Hochschild homology of the category D over C. So these are the analogs in the setting when C is the chain complexes are listed on the right, where the definitions on the left correspond to just exactly the familiar definitions on the right. So smoothness is perfect, the diagonal bimodule being perfect. Properness is the morphism spaces being perfect. You can read the definition of a Calabi Yau structure. This is the proper Calabi Yau structure that I wrote here. And there's the usual Hochschild homology for DG categories. So all these things just have analogs in the more general setting.
Could you remind me mod sub E?
Could I remind you what?
The mod sub E for your definition of a link cut over E.
It's not E, it's C.
Oh, it's C. Mod sub. So what is that?
It just means module. Okay, so C was a symmetric monadal category, which you can think as a monad object in the category of pre-stable category with this Lurie tensor product. And D can just be thought of as a module over this monad object. That's what mod means. So it's module over C. Okay.
So monoidal structures, it's kind of product, analog of the product on algebra. You have the standard and so then if you have a monoidal category even without this infinity, blah, 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 you can try to speak about modules of this symmetric monoid, or not necessarily symmetric monoidal category. It's sort of an infinity version of this stuff.
Yeah. Yep. Okay, and just one note. So you'll notice that I have mentioned that the Hochschild homology actually lifts to a symmetric monadal functor. So initially, Hochschild homology of D is just an object in C, but you can actually show that this lifts to C to the power BS1, which is supposed to represent objects of C equipped with a coherent S1 action. So Hochschild homology as a functor can be lifted from something valued in C to something valued in C equipped with action of S1. Okay, so we are going to refer to this fact later on. So I just mentioned it here. Okay, so this is just analogs of usual definitions from DG setting. Slightly more abstract nonsense definition. So this is the only definition we need related to duality. So I want to define what we mean by a dualizable object. So if you have a symmetric monadal category, we say that an object in this category is dualizable if there exists a dual object called C check equipped with an evaluation map that goes from C tensor C check to the monadal unit and a co-evaluation map that goes from the monadal unit to C check tensor C, such that these evaluation and co-evaluation satisfy the usual snake relations that might be familiar, for example, from definitions like Frobenius algebra. And something to note here is you only demand these relations hold in the homotopy category. So you don't literally want them, you don't literally need them to be identity, they are homotopic to identity. Okay. So for example, if you apply this definition to the category of chain complexes, then a dualizable object is exactly a perfect complex, which is a complex whose total cohomology is finite dimensional over K. Okay. So this is what we mean by dualizable object. And you can talk about such an object whenever you have a category with a tensor product. So in particular, you can talk about dualizability of an object in CBS1. So these are objects of C equipped with a coherent S1 action. Okay. Any questions on this? Okay. So let's actually, I gave most of the background, so let's actually begin with the construction. So I'm going to follow here the setting in Costello's paper because it's useful to say the universal property. So this is the Costello. So Costello's construction also again goes in two steps. So the first step is an equivalence between open TCFTs and Calabi Yau categories. So open TCFT valued in a symmetric monadal category C is equivalent to Calabi Yau category in linear over C. And this equivalence roughly is just exhibited by taking a TCFT. So remember, this is a monadal functor from M-framed open into C, and you just restrict this functor to the subcategory given by genus 0 surfaces. So surfaces with one output, like the one drawn on the left, give you the composition of morphisms in this category. And the Calabi Yau structure roughly comes from the surfaces that I draw on the right. So on the right, it's supposed to kind of give you a map from the Hochschild homology of the category to the ground field. Okay, so this is Costello's first statement that open TCFTs are the same data as a Calabi Yau category. Costello's second statement tells you how to define a positive boundary open closed TCFT from an open TCFT. So once you have a positive boundary open TCFT, which means that a functor out of this positive boundary M framed, you can restrict it to an open TCFT. And this restriction has a left adjoint where you just given an open TCFT, you freely extend it to a positive boundary open closed TCFT. So this free extension is homotopy initial in the category of all extensions of your open TCFT. Okay, that's what free extension means. So Costello's theorem has two important points. The first is he actually computes the value of this free extension on the circle, on the object with a single closed input and no open input. And secondly, he actually shows that this extension is symmetric monadal. So you do actually, like, if you just start with a functor and freely extend it, it need not be symmetric monadal. But to get something which is positive boundary, you actually need something to be you need the extension to be symmetric monadal. And Costello shows that it's symmetric monadal. So these are like two important things about Costello's statement, that this free extension is actually symmetric monadal, and the value of the free extension on circle is given by Hochschild homology of the underlying algebra. Okay, and as I mentioned, this free extension is homotopy initial in all extensions of your given open TCFT. So this is the universal property that we are going to use later on to make comparisons. And this universal property forces you to work in some setting where you can talk about homotopy universal properties. And that's why, as I mentioned, we work in this infinity category setting. So are there questions about these statements?
Yeah, I know it, but in a different language, which
Yes.
is less heavy and maybe more transparent, but basically, yeah.
Yeah, I think...
Actually, so when you're giving this link category over C, and you said the Calabi Yau in that category, is that category of a Calabi Yau objects, or?
Yes.
And so that category itself is a monoidal. Does it have some how to say what the objects in that category is Calabi Yau? You look at all the dualizable objects, or?
Yeah, I mean, there's a definition of what Calabi Yau means, and I didn't give you the definition, so I'm...
Okay, I see.
Yeah, you can if you think of chain complexes, this just means Calabi Yau categories on the right.
But those are the modules over C. The objects are modules.
Less trivial example is an algebra with a bilinear form. Something which you know very well. Algebra with a scalar product. It's sort of a toy model for Calabi Yau.
The link are modules over the model category C. So they are not algebras.
Well, actually, there is no big difference because when you have smooth proper, I mean, sometimes you can choose a generator, so your category will be the category of infinity modules or some infinity algebra. If it's Calabi Yau, there is a scalar product on it, and so that's, if you assume that it's just one algebra, it will be easier to understand what's going on. I mean, it's more complicated language, but sometimes if there are too many words, it's kind of.
Yeah, just want to get a sense where how the Calabi Yau, this kind of a serial-duality type.
No, it's not. Well, there are first of all there are several definitions what Calabi Yau structure is. It's better to think that it's third duality is a pairing, yeah, so it's like scalar product. So that's maybe easier than third duality in the sense of textbooks, yeah. And the scalar product allows you to go from genus 0 to arbitrary genus. So that's how it works.
Yeah, so the proof of this fact is already whatever was in papers of Seibelman and Costello, but it just works in more general setting. So recently there was some work of Barkan, Steiner-Brunner, and John, who did this in this most general setting, valued in these infinity categories, but the underlying geometric ideas are same as the original proofs. Okay, so this is the first step of the construction, which is how to go from. So this construction actually doesn't even require the smooth part. You just need proper Calabi Yau category, and you can get a positive boundary TCFT. Okay, so this is the first arrow. So now I need to tell you second arrow, which is to go from positive boundary TCFT.
Proper corresponding to the similar to the complete variety or projective variety. Is that what a proper mean?
Yeah, exactly.
Yes, yes.
Okay, yeah, thank you.
Yeah, so as I was saying, the next part is going to be how to go from positive boundary TCFT to actual TCFT, which means removing this at least one input condition. So that's the next statement. Okay, so here I say that you look at space of all full TCFTs valid in C without this at least one input condition. And I express this space as some fiber product. So let's try to decode the fiber product. There are three things. First is this positive boundary TCFT. The second is, you'll see that I have two categories. One is pairing CBS1, and then there's CBS1 dualizable. So CBS1, as I mentioned, is just objects of C equipped with a coherent S1 action. So CBS1 dualizable just means that you restrict to dualizable objects in CBS1. So remember, dualizable objects are these objects with evaluation, co-evaluation satisfying the snake rule. And you look at these dualizable objects in the category of objects of C equipped with S1 action. The next category over which the fiber product is actually happening is just what I'm calling pairing CBS1. I don't think there's any standard terminology, but it just means that it's a choice of two objects in C and a pairing between them. So it's evaluation from A tensor B to the monadal unit. So just two objects with a pairing. So how do we take the fiber product? What are the maps? So remember, once you have a dualizable object in C, it comes with a pairing and co-pairing. So there was a typo here. So here it should be dualizable in BS1. Here also BS1. Okay. So I was describing what are the maps that go into this fiber product. So the first map is from CBS1 dualizable to pairing CBS1. So if you have a dualizable object, by definition, it comes with this A dual, evaluation A and co-evaluation A, because that's what means to be dualizable. And you just forget from this object, forget the co-evaluation, map it to evaluation. That gives you a map from dualizable objects to this pairing CBS1. So that's the first map. The second map is from positive boundary TCFTs to pairing CBS1. And this is maybe the more interesting map. So let's say you start with positive boundary TCFT. Then if Z is your functor, which is a functor out of positive boundary and framed into C, then you map it to Z evaluated on the circle. And this object, Z evaluated on circle, actually comes with a pairing just from the TCFT structure, because you can take the map given by the cylinder with two inputs, and this gives you a map from Z evaluated at circle tensor Z evaluated at circle into the monadal unit, just from definition of what it means to be a functor. So this is the map that you get from a TCFT into pairing CBS1. Any TCFT evaluated on the circle gives you an object with a pairing in an S1 equivalent way. And that's the map on the bottom. And the vertical map is just, if you have a dualizable object, then you get an object with a pairing. Okay. So this is how the fiber product is constructed. Let's actually see what the fiber product is saying. The fiber product is supposed to tell you how you can extend an object, how you can extend a positive boundary TCFT to a full TCFT. Namely, you take your positive boundary TCFT and you look at the value of the TCFT on the circle equipped with a pairing coming from this cylinder. And if this pairing extends to a dualizing, if this pairing is a dualizing pairing, meaning there's a co-pairing which makes the object into a dualizable object, then your TCFT actually extends to a full TCFT. Okay. So something important to note about this statement is that the statement actually tells you that extendability to extendability from a positive boundary TCFT to a full TCFT does not require more data. It's a property. So it's a property to be extendable to a full TCFT. You don't need more data. Because once you have a pairing, there's essentially a contractible way of extending this to a part of a dualizing datum. So are there questions about this part? Okay. So this is the statement that tells you how to go from a positive boundary TCFT to a TCFT. Namely, you just need to check whether your TCFT gives a non-degenerate pairing on the value of the TCFT on the circle. And if it does, then it extends in a contractible way. So here's a fact that we can actually use in the case of chain complexes. Namely, if you have a smooth and proper DG category over K, then the Hochschild homology of the category is actually dualizable in chain complexes with circle action. So if you start with a smooth proper Calabi Yau category and you apply Costello's construction, it gives you a positive boundary TCFT. And this fact is telling you that the value of the TCFT on the circle is dualizable in chain complexes with S1 action. So the theorem actually tells you that you can extend to a full TCFT in essentially a unique way. Okay. Is there a question so far? Okay. If not, I'll go ahead. So this was the second arrow in second step in the construction, and we now come to the last step, which tells you how to go from a full TCFT to a DMFT. So going from this field theories where morphisms were smooth Riemann surface to going to a field theory where morphisms are used in Mumford spaces. Again, in this case, how to do this is encoded in terms of a fiber product. So you look at space of all DMFTs valued in C, and this is expressed as a fiber product. So the fiber product involves three things: a TCFT, then you have CBS1, so C with objects of C with S1 action, dualizable objects in this, and then you just have C dualizable, so just dualizable objects of C. And you're supposed to take some tensor fiber products. So what are the maps in the fiber products? So first, let's consider the map from C dualizable to CBS1 dualizable. And the way you get this is, if you have an object of C, you can consider it as an object of CBS1 by just equipping it with a trivial S1 action. And that gives you a map from dualizable objects in C to dualizable objects in BS1, CBS1. So that's this vertical map. The horizontal map is the map from TCFTs to CBS1 dualizable. And the map is, again, you take a full TCFT and you just evaluate it on the circle. So now in this case, you have these two operations as part of the TCFT now. So remember, there's no positive boundary condition. So both these cylinders are part of your TCFTs. And these things actually give you evaluation, S1 equivariant evaluation and co-evaluation map on Z of the circle. And this tells you that Z evaluated at circle is a dualizable object in CBS1. So that's this horizontal map from a full TCFT into C with S1 action, dualizable objects in C with S1 action. Okay, so these are the maps that you use to form the fiber product. And what is the statement actually saying? So the statement is saying that the space of DMFT is the same as this fiber product, which means that if you start with a TCFT, if you want to extend it to a DMFT, you do the following: you take the TCFT, you evaluate it on the circle. So you land in CBS1 dualizable object in CBS1, and you ask whether this thing can be lifted to C dualizable, namely whether this S1 action on the dualizable object is trivializable, because that's what lifting along this vertical map means. If you have object below and you can lift it to object above, that just means that it is isomorphic to an object with trivial S1 action. So extending from this TCFT to DMFT, you just have to check whether the value of the TCFT on the circle actually comes from some object with trivial S1 action. So this is this intuition that if the S1 action on Z evaluated at circle is homotopy trivial, then you actually have an extension to DMFT. So I think this was known for a long time. People were using it to construct categorical invariant, but I don't think there was a statement of getting a DMFT.
But did people construct a DMFT before you?
I don't think so.
Yeah, so then maybe that's explanation why they didn't use this homotopy.
Yes.
Yeah. Yeah. Because for people who hear all that stuff for the first time in their life, I think it's impossible to understand what's going on.
Yeah, unfortunately.
Yeah, too many words without clear geometric meaning. It's kind of pretty dry. Yeah.
Yeah.
Yeah, anyway, go ahead.
Okay. So, yeah, so this is the construction for a DMFT starting from a TCFT. And how do you actually check these things in practice? Because remember, we are working in some homotopy coherent settings. So even saying that an object in CBS1 lifts to C, you need to give infinitely many pieces of data in order to construct a trivialization. So how you do it in practice? So turns out that there's a very easy, well, not there's a very concrete criterion to check. And I mean, in this setting, in this homotopy coherent setting, it's in one of the papers of Akhil Mathew, where he says that if you start with a module equipped with an S1 action, then this module admits a lift to module over K. So module which a priori lives in module BS1 admits a lift to module K if the fixed point S1 fixed point spectral sequence splits. And moreover, the space of such lifts is homotopy equivalent to the space of splittings. And also, I mean, remember, we want to do this, like we want to construct these lifts in dualizable objects. So you want space of lifts that preserve certain pairings and space of lifts preserving pairings, same as space of splittings preserving natural pairings on these these homotopy groups. So usually, I mean, this spectral sequence here is just what's usually, in case of chain complexes, what's usually called the Hodge de Rham spectral sequence. So getting this homotopy coherent lifts can be just done by looking at the splittings of the Hodge de Rham spectral sequence, which is something cohomological. So to get this data, going from a TCFT to DMFT, you have to check something cohomological. So it's not completely impossible to do it in practice. Okay, so this was the story of the construction, and I'm already actually over time. So this is how you construct a DMFT starting from a smooth proper Calabi Yau category. You first apply Costello's construction, get a positive boundary TCFT. You look at value of the TCFT on the circle and see if the pairing that the TCFT gives you is non-degenerate. If it's non-degenerate, there's a natural extension to a full TCFT. And then you see whether the S1 action on the value of the TCFT on the circle is homotopically trivial. And if you choose such a trivialization, the choice gives you an extension to a DMFT. So this is the full construction. If there's any questions, I'll wait.
I think that's what we did in less generality, because we did not work with presentable infinity categories, but at the level of the action of a certain chains of the prop. So it's exactly what's going on. So this triviality, if you look at the level of chains on like Hochschild chains on the Calabi Yau category, so then there is an action of chains on the prop of this framed, in your language, framed Riemann surfaces.
Yes.
And if you want to extend it to cohomological field, so that's already topological field. So then if you want to extend it to cohomological, you need the generation of Hodge de Rham, which in the language of original language of Alan Kohn means that you have double complex, as you say, spectral sequence, double complex with two differential. One is Hochschild and another one is Kohn differential. And Kohn differential is exactly the action of the circle. So this homotopy triviality means that cons differential X trivially on the Hochschild homology. So
Yes.
then you extend it to what you say is stable, whatever. Anyway,
Yeah.
you extend it to a slightly different prop where the action of the cylinder is trivial.
Yes.
Yeah, okay. Yeah, but you have more generality, so you develop your more general language, which of course probably people are overwhelmed, at least I did. Yeah, all right. So you mentioned also another homological field theory, which you called Gromov Witten.
Yeah, so if I can
Maybe just, I understand you over time, but maybe you just briefly say what is it?
So, okay, so here's let me try to state the comparison statement. So the kind of geometric DMFT we are going to want is of the following nature. So you have a closed symplectic manifold. You want the open-closed DMFT so that its open part is same as the genuine Fukaya category, no curvature. It's a Fukaya category in chain complexes. And the Calabi Yau structure that corresponds to this DMFT should be just the Poincare Calabi Yau structure. That's the first condition. The second condition is if you look at the homology that you get from this DMFT, the homology should correspond to Gromov Witten DMFT. So DMFT that you just get from counting curves. And there's an open-close map which goes from the Hochschild homology to the value of your geometric DMFT on the circle. And this open-close map should be an isomorphism on homology. So this is the axiomatic framework where you assume that there's some other geometrically constructed DMFT with the same open sector and the open-close map being a quasi-isomorphism. Then you trace through these various statements that I described to eventually conclude that the categorical DMFT you get has to coincide with this other DMFT that you constructed by any method, just from some universal property. So the splitting that feeds into this categorical construction is something that you can just take from the geometric construction, because these fiber product statements that I mentioned, they go both ways. So they tell you how to do an extension, and if you have an extension, they also tell you what data that extension corresponds to. So since we have an extension on the geometric side, that gives you a splitting, and you can fit that splitting into the categorical construction to get a categorical DMFT. And the universality properties tell you that these DMFTs have to coincide with the geometric one.
Okay, yeah.
So that's just an application of universal properties. But in terms of actual geometric constructions, there's so far what we have is this work of Hirschi-Huchtenberg from earlier this year, where they construct open-close DMFT in the case of a single, like objects supported on a single Lagrangian. So you have branes, all the open branes are supported on a single Lagrangian. This construction uses de Rham forms, so it works over real numbers. It's filtered, meaning like it's filtered by energy of the curves. So at a time you only consider finitely many curves. It's curved because this you cannot avoid in general. But to do these categorical constructions, you need an uncurved theory. So I think that's not there yet. We don't know how to algebraically do this. I guess one nice thing about this construction is it's strictly symmetric, strictly cyclic. I think in general, when you have more than one Lagrangian, maybe we don't expect it to be strictly cyclic. And maybe most importantly, this DMFT is actually missing some parts. So these disks that I mentioned here, which is disk with one output and disk with two outputs, are missing from the geometric theory. So like as it is, you cannot use it to get a DMFT in the sense that I mentioned in the construction, because these two operations are missing. Even if you artificially insert them by hand, you would have to construct infinitely many compatibilities. So it's not entirely clear how this is going to go. But to feed it into the construction, you would need the entire open-closed DMFT. So this is the state of the geometric construction that's available so far. I think I will stop unless there's more questions.
Yeah. Okay. Thank you very much. Now, are there any questions?
So what was the problem with the curvature you were mentioning with this construction?
I think you need some strict unitality in order to get rid of the curvature to get a genuine DMFT.
Yeah.
So that's not available, I think.
But their construction is strictly unital, right?
I'm not quite sure. Maybe I need to look at this again. Last time I checked, these things were not strictly unital, but maybe I'm wrong.
Okay.
More questions?
Earlier, in your definition of this category MOC, you pair finite sets once
Yes.
C and O. What does O and C really mean?
O and
what's
C.
the motivation?
Open, closed.
Yeah, it just means open and closed.
Ah. Okay.
Okay. More questions? Well, if there are no more questions, so thanks again for a very interesting talk. And
thank you for.
Yeah, thank you. And this is it for today. You see a lot, a lot of applause from the audience. All right, thank you very much. And this is it for today. And I